The following question reads that element sodium to sulfur react with chlorine. The melting point of some of the chlorides formed are shown. So you have NaCl, MgCl2, AlCl3, and all of them given. So these are all PD3 chlorides, and their melting points are given. In the first part, option A, predict the shapes of AlCl3 and PCl3. Draw diagrams to show the shapes, name the shapes, and state the bond angles. So starting with AlCl3, the shape is going to be, for AlCl3, the shape is going to be trigonal planar. It only has 3 bonds. So there's going to be a Cl over here, one Cl at 120 degrees, and another Cl at 120 degrees. All the angles are going to be 120 degrees. So it's going to be fan shaped. The shape would be called trigonal planar, and the angles are going to be 120 degrees. So this is how 3 bonds, shape of 3 bonds, molecules that have 3 bonds or 3 bond pairs, it's going to look like. It's going to be fan shaped and it's going to be completely flat. It's going to be planar. Then we draw the shape of PCl3. Now again, PCl3 has 3 bond pairs, but the problem is that phosphorus has a lone pair. So the bonds, although they're going to look fan shaped, but the fan would be bent downwards because of the repulsion from lone pairs that are sitting on the top. So phosphorus is in group 5, which means it's sharing 3 electrons and 2 electrons. A lone pair is left at one end, and because of the repulsion of these lone pairs, the 3 bonds are going to be bent downwards and the angles would decrease. It's going to be, the angles would be 107 degrees, and the shape would be called trigonal pyramidal. So it's going to be in the form of a pyramid. All the 3 bonds are going to be bent downwards with the lone pair sitting on top, causing the repulsion so that all the bonds are repelled downwards and have an angle of 107 degrees. Moving now to the next part of the question. The next part of the question is, explain in terms of structure and bonding why the melting point of SiCl4 is much lower than that of NaCl. I'm going to first comment on NaCl, which is a giant ionic lattice. So there will be lots of positive and negative ions, and they would all be connected to each other. So explain in terms why the melting point of NaCl is higher. First reason, it's a giant ionic lattice. And the giant ionic lattice consisting of positive and negative ions, where there's strong electrostatic attraction between positive and negative ions. Which is why more energy is needed to melt it. All the positive and negative ions, Na plus and Cl minus 1 ions, they would be attracting each other very, very strongly. So this is why NaCl is going to have a higher melting and boiling point compared to SiCl4. Let's look how the structure of SiCl4 is going to look like. The structure of SiCl4 that I've drawn over here is going to be simple molecular, where you would have small molecules like Si bonded to 4 Cls, and that's it. It's not a giant structure, it's just a tiny molecule, and there's going to be another molecule of SiCl4, and the 2 molecules are going to have very weak attractive forces between them. They would be very weak intermolecular forces. In this specific case, since both molecules are non-polar, SiCl4 is non-polar, SiCl4, this other SiCl4 is also non-polar. So they're going to be very weak van der Waals forces between them. So the melting point is going to be very less, because very less amount of energy would be needed. So SiCl4 has a simple molecular structure and with weak van der Waals forces between molecules. So it's very easy for the less amount of energy would be needed to overcome these intermolecular forces and to melt the substance. So SiCl4 has a lower melting point. Moving to the next part of the question now, you're being asked, explain why the melting point of SiCl4 is higher than that of PCl3. So you have 2 molecules and again they're both simple molecular structures. You'll have SiCl4 molecules as I have shown over here, and then you're going to have PCl3 molecules. So here you can see 2 PCl3 molecules, and they would also have intermolecular forces. But as you can see, SiCl4 is a bigger molecule. PCl3 only has 3 chlorines, whereas SiCl4 has 4 chlorines. So if the molecule is bigger, so the first point would be SiCl4 is a larger molecule, and has greater MR. So if a molecule is bigger, it has more electrons, which leads to more van der Waals forces. So hence, more van der Waals forces will be present in SiCl4. The van der Waals forces are temporary dipole induced dipoles. Molecules would have electrons that would be fluctuating, resulting in partial negative and partial positive charges randomly. They would be temporary dipoles, induced dipoles, partial negative, partial positive size. Electrons might be, the molecules are bumping around, so the electrons in the molecule would be randomly just getting knocked side to side. So partial negative, partial positive charges would be produced in one molecule. The same would happen to the other molecule, and the two molecules would be attracted to each other because of van der Waals forces. Now, if the number of electrons are more, then the size of the partial negative and partial positive charges, the temporary dipoles that are produced, they're going to be greater, and the attraction is going to be greater. This molecule is smaller, so it has fewer number of electrons. So there's fewer, lesser partial positive, partial negative sides being produced. So the van der Waals forces in this molecule are going to be lesser. In this question, in part 3, you have to draw the dot and cross diagram of SiCl4, showing outer electrons only. Now silicon is in group 4, and chlorine is in group 7. So chlorine only shares 1 electron, silicon shares 4 electrons. So here I've drawn the dot and cross diagram. This is silicon in the middle. It has 4 electrons. It's going to share 4 electrons with each of the chlorines, and chlorines are going to share just 1 electron. They're in group 7, so they share 1 electron. So these are all Cl atoms. Now chlorine has 7 electrons in its outermost shell. It shared 1 electron, so you're left with 6 electrons. So there would be 6 electrons left in each of the 3 lone pairs in each of the chlorine atoms that are bonded to silicon. So this over here is your complete dot and cross diagram for SiCl4. The following question reads that at 450 kelvins, PCl5 decomposes to form PCl3 and chlorine. A dynamic equilibrium is established as shown. So you have this reaction happening where PCl5 is changing into PCl3, Cl2, and vice versa. So it's going in forward and backward direction at the same rate. Now the enthalpy change for formation of PCl3 under these conditions is given. So you are given the enthalpy of formation of PCl3. Calculate the enthalpy change of formation of PCl5 under these conditions. Include a sign with your answer. Now, one method of calculating the enthalpy of a reaction, of this particular reaction, remember we already have the answer. The enthalpy change for this reaction is already calculated. But one way of calculating the enthalpy of this reaction is using Hess law, is that if you're given the enthalpy of formation of the products as well as the enthalpy of formation of the reactants, so you can use a simple formula, which is that the enthalpy of this reaction could be calculated by summing up the enthalpy of formation of products and subtracting the enthalpy of formation of my reactants. So if the enthalpy of formation of everything is given, all the products and all the reactants are given, I can calculate the enthalpy change for that particular reaction using this formula, and this is precisely what I'm going to do. What I'm going to do is I have enthalpy of PCl3 is already provided. It's given as minus 320. So the enthalpy change, which is already known, it's 124. I have the answer, it's plus 124. So I'm going to sum up the enthalpy of formation of my products, which in this case are PCl3, which is minus 320, plus the enthalpy of formation of Cl2. Remember, Cl2, the enthalpy of formation of elements is always 0, because you don't need to form elements. Elements are already in their formed state, so you don't need to do anything. So enthalpy of formation of elements is 0. So these two are my products. So this is my products, or the sum of my products. And I'm going to subtract my reactant, enthalpy of formation of my reactant, which is supposed to be calculated. We had to calculate the enthalpy change of formation of PCl5. We don't have this value, so I'm going to take this as the unknown, the enthalpy of formation of PCl5, and I don't have a value for that. So this is my reactant. So it's going to be product minus reactants, the enthalpy of formation of my products minus the enthalpy of formation of my reactants, and I already know the enthalpy change, which should come out to be equal to 124. Now, rearranging everything, I'm supposed to find the enthalpy of formation of PCl5. So let's rearrange everything. PCl5, enthalpy of formation of PCl5 would then be equal to, it's going to be equal to minus 320. And if I take 124 to the other side, it's going to become equal to minus 124. And my answer is going to be, so the answer is minus 444 kilojoules per mole. Let's move to the next part of the question. The next part of the question now states, B part 1, state and explain the effect of increasing temperature on the rate of decomposition of PCl5. So we need to explain the rate of increasing temperature. Remember, whenever you increase temperature, this question is not about anything else, not about equilibrium, it's about the rate of the reaction. So a lot of people confuse this with equilibrium and with many other things. So it's a simple statement. If you increase temperature, what happens to the speed of the reaction? So the answer is that when you have a higher temperature increases kinetic energy. So if it increases kinetic energy, particles are going to travel at a faster speed. So they're going to have more frequent collisions. The amount of or the frequency of collisions would increase. You'll have more particles bumping into each other. Plus the percentage of effective collisions also increases. The collisions are going to be more forceful and there are more chances of a successful reaction happening. So higher temperature increases kinetic energy and you get more frequent and more effective collisions. Now moving to the next part of the question now states, state and explain the effect of increasing temperature on the percentage of PCl5 that decomposes. Now this part is you're increasing temperature and the question now specifically is talking about the equilibrium. Remember, increasing temperature always favors the endothermic reaction. So the endothermic reaction is supposed to be favored if you increase temperature. Now let's go above and have a look at the reaction. You will notice that this reaction over here, the value that's given is the enthalpy change for this particular reaction is given as plus 124. That's endothermic, which means that the forward reaction, the reaction is endothermic in the forward direction. The enthalpy change is always given for the forward reaction. So the forward reaction is endothermic. And we have already stated that whenever you increase temperature, according to Le Chatelier's principle, it's the endothermic reaction which is going to be favored. Hence, in this particular case, forward reaction would be favored. So forward reaction is going to be favored. And we need to talk about or comment on the percentage of PCl5. So if you go back and have a look, if the forward reaction is favored, then more PCl5 will decompose. So the amount of PCl5 at equilibrium would decrease. So the percentage would be lesser. So PCl5 decomposes and the percentage of PCl5 at equilibrium would be lesser as more forward reaction takes place. Moving to the next part of the question, now you are being asked, explain the meaning of the term dynamic equilibrium and the conditions necessary for it to become established. So the first thing I'm going to do is I'm going to write down the definition of dynamic equilibrium, which is that the rate of forward reaction equals the rate of backward reaction. So for example, if you have an equilibrium reaction, the rate at which the products are being formed and the rate at which the reactants are formed back again, both rates would be equal. The quantities of all the reactants and products could be different, they could be the same, but the condition is that the rate of forward reaction equals the rate of a backward reaction. So let's write that down. So here it's written when the rate of forward reaction equals the rate of backward reaction. And the other thing that should be noted is the conditions necessary for it to become established. The container must be sealed or closed, or you must ensure that there are no changes in conditions of pressure, concentration, or any other changes that should be introduced to the system. The container must be, it's supposed to be a closed system. Part D now reads that when 2 moles of PCl5 are decomposed at 450 Kelvins and 1 into 10 to the power 5 pascals, the resulting equilibrium mixture contains 0.8 moles of chlorine. So we need to calculate the partial pressure of PCl5 in this equilibrium mixture. So I've drawn a table, and this was the equilibrium reaction where PCl5 was decomposing to form PCl3 and Cl2. And this reaction is at equilibrium. The forward reaction and the backward reaction are happening. So I'm going to first find out the initial moles, the moles that were in the beginning added to the container. So you notice when 2 moles of PCl5 are decomposed, your initial moles for PCl5 are 2.00 moles of PCl5. The moles of PCl3 are 0 moles, and the moles of Cl2 are also exactly 0 moles. So initially there's only PCl5. And then it decomposes, and the resulting equilibrium mixture. So let's write down the moles at equilibrium. At equilibrium, the equilibrium moles that are given or provided. The equilibrium moles are provided for Cl2. It's given that it's 0.800 moles of Cl2 that are present at equilibrium. Now, if you look at this table, initially there was no chlorine, and now 0.8 moles of chlorine are present. That means 0.8 moles of chlorine have been formed. So if 0.8 moles of chlorine have been formed, PCl5 was decomposing. It was going to produce PCl3 and Cl2. So Cl2 would not be formed in isolation if the moles of PCl3 and Cl2 would be exactly the same. So if 0.8 moles of Cl2 are formed, then according to the ratio, it's 1:1. The amount of PCl3 that's going to be formed would be exactly the same as well. So 0.8 moles of PCl3 would also be formed. And if 1 PCl3 is formed, according to the ratio, 1 PCl5 would get used up. So if 0.8 moles and 0.8 moles of both of these products are formed, that means 0.8 moles of PCl5 must have reacted. So 0.8 moles must have reacted. So initially you had 2 moles, and we figured out that 0.8 moles of PCl5 have reacted. That would leave us with 2 moles initially, 0.8 reacted, so that leaves us with 1.20 moles of PCl5 at equilibrium. And similarly, initially you had 0 moles of PCl3, 0.8 moles got formed, so at the end it's going to be 0.8 moles. So I found the equilibrium moles of all the 3 substances. It's 1.2 moles, 0.8 moles of PCl3 and 0.8 moles of Cl2. So let's put this to the side for a while. We now have to find the partial pressure of PCl5. How do you find PCl5 partial pressure? The formula is you first have to find the percentage mole or mole fraction and multiply it by the total pressure, which is which over here is given. It's 1 into 10 to the power 5. So we need to multiply it by the total pressure. So what's the mole fraction? Remember, all of these moles combined, especially the ones at equilibrium, all these moles, these are the moles that are present at equilibrium. So all these moles, all of these gases combined are exerting a pressure of 1 into 10 to the power 5. So what is the contribution of PCl5? So out of all these moles, PCl5 is 1.2 moles. So I'm going to add them up. It's 1.2 moles. The mole fraction is 1.2 moles out of the total moles, which over here is going to be 1.2 plus 0.8. That's 2. 2 plus 0.8 again. That's 2.8. So it's going to be 1.2 divided by 2.80, and I'm going to multiply it by the total pressure, which in this case is 1 into 10 to the power 5. And the answer that I'm going to get is, on my calculator, it's coming out to be 4.29 times 10 to the power 4 pascals. So that's the answer that I am getting on my calculator. Let's move to the next part of the question, where we now have to write the expression for the equilibrium constant Kp for the decomposition of PCl5. So if you look at the equation, it's products, the partial pressures of the products divided by the partial pressure of my reactant. So I'm going to do just that. My products are partial pressure of PCl3 multiplied by the partial pressure of chlorine. Those are my products divided by my reactants, which in this case are partial pressure of PCl5. In the next part, what is given now is that the partial pressure of PCl3 and Cl2 in this equilibrium mixture are both 2.86 into 10 to the power 4 pascals. We now need to calculate the value of Kp and state its unit. So what I'm going to do is I'm just going to substitute these values over here. These values are given for PCl3 and PCl2. Both of them are given. So let's do a working over here. It's going to be 2.86 into 10 to the power 4 multiplied by 2.86 times 10 to the power 4 again, because he has clearly stated that both PCl3 and Cl2 in this equilibrium mixture are both 2.86 into 10 to the power 4, and I'm going to divide it by the partial pressure of PCl5, which I've already calculated just above. It has been calculated as 4.29 times 10 to the power 4. And if you try and solve this, the value that I'll be getting is 1.91 into 10 to the power 4. So this would be the answer to this part. Calculate the value of Kp. So we've precisely done just that, and we also need to find the unit. So you can figure out the unit by looking at the expression. This is pressure multiplied by pressure divided by pressure. So two of the terms, if I try and calculate the unit, it's going to be pascals multiplied by pascals divided by pascals, and the pascal term would cancel out, and my unit for Kp would be just pascals. So it's going to be just pascals. So it's going to be 1.94 times 10 to the power 4 pascals. The following question reads that the element in group 2 show trends in their properties that are typical of metals. The elements of group 17 show trends in the properties that are typical of non-metals. So state and explain the trend in ionization energy down group 2. So we're talking about removing electrons, so we have to discuss the trend in ionization energies down group 2. So I've drawn over here the example of beryllium and magnesium. I've also answered the question, but let me first explain to you. As you move down the group, the number of valence electrons remain the same, but the shells keep on increasing. So what happens is that ionization energy, what is ionization energy? It's the energy required to remove an electron. So since these electrons are closer to the nucleus is right in the middle. So there's a positive nucleus right in the middle. So if the atom is smaller, electrons are very close to the nucleus and there's less shielding effect. But as you move away from the nucleus, the electrons are now further away from the nucleus, and there are lots of electrons coming in between the nucleus and these outer electrons. So what happens is that ionization energy decreases down group 2. Because atomic radius increases, you have bigger atoms, it becomes easier to lose electrons. And shielding effect also increases. These outer electrons and the nucleus, there are lots of electrons coming in between. So they're going to shield the nucleus, and the attraction for the outer electrons would decrease. So it's going to become easier to remove an electron. So ionization energy would decrease down group 2 because atomic radius increases and shielding effect also increases. Now moving to the next part of the question, which is part B, state and explain the trend in melting points down group 17. So group 17 is fluorine. So you have a molecule of fluorine, you have a molecule of chlorine, then you have a molecule of bromine, and so on. This is a gas. The first one is a gas. The second one is also a gas. The third one is actually a liquid. It's a red-brown liquid. And if I draw iodine at the bottom, that's a solid. So one thing that you can notice is that the melting points increase. They increase down the group. Things are becoming more solid. So melting points are increasing. So they increase down group 17. And what's the reason for the increase? Remember, these are simple molecules. You'll have a molecule of fluorine and you'll have another molecule of fluorine. Now, fluorine molecules are non-polar. So, for example, over here I've drawn two fluorine molecules. Fluorine molecules are non-polar. They don't have permanent dipoles. The only force of attraction between them is going to be van der Waals forces. So melting points increase down group 17 because van der Waals forces, or you can call them temporary dipole induced dipoles, they increase as down the group you have bigger molecules. As molecule size increases. So why do van der Waals forces increase? Because as you move down the group, the molecule has more electrons. So there's the more chances of temporary dipole induced dipoles being formed. For example, iodine over here has a total of around 100 electrons. So if 100 electrons fluctuate, move left and right in random fashion, the temporary dipoles that would be formed would be very strong. Fluorine just has 18 electrons in total. This molecule over here has a total of 18 electrons. So if 18 electrons fluctuate randomly in collisions, the partial negative and partial positive charges are not going to be very strong. So the attraction between one molecule and the other molecule is going to be weaker in the case of fluorine, but very strong in the case of iodine. Moving now to the next part of the question, which now states the melting point decreases down group 2. And we have to explain this trend. The first thing you should know is that group 2, they're all metals. So we're talking about metallic bonding. Now I've drawn the structure of a metallic bond. In metallic bonding, it's a giant metallic lattice where you have lots of positive metal ions. Metals like to lose electrons, so they all form positive ions, and there would be delocalized electrons around them, and there would be attraction between the delocalized electrons and the positive metal ions. So what happens as you move down the group? The only difference that's going to happen is, remember, group 2, all the metal ions would have a charge of +2, and each metal ion would have 2 electrons. They would be lost or delocalized. 2 outer electrons would be lost in group 2. So this applies to the entire group 2, whether it's barium or calcium or magnesium. The positive ion would always be +2, and there would be 2 electrons that would be delocalized by each atom. So what happens as you move down group 2, the only difference would be that the size of the atom or the size of the ion is going to be bigger. So here I've drawn a similar metallic lattice. The only difference now is that the size of the ion, as you move down the group, the size of the ion is going to be bigger. Down the group, the size of the atom increases. There are more shells. So you have a bigger giant ionic metallic lattice. Over here, the bonds are going to be weaker because it's the same number of electrons, delocalized electrons, and the charge of the ion is still +2. The attraction between the ions and the electrons would be lesser because of the bigger size. The distances have now become greater, so the attraction would be weaker. Over here, the distances between the ions and the delocalized electrons was smaller, so the attraction between the ions and the delocalized electrons was stronger, which is why metallic bonding would be weaker for bigger ions. There would be greater distance, lesser attraction, so metallic bonding is going to be weaker for bigger ions. And this is what we are going to write why the melting point decreases, because the metallic bonding and its strength decreases because of the bigger ions. So I've written the statement, which is that down group 2, ionic radius increases, specifically cationic radius increases, and there's lesser charge density of the metal ion. Bigger ions, the positive charge would be more distributed, so there's going to be lesser charge density and lesser attraction between metal ions and the delocalized electrons, so weaker metallic bonds would be present, which is why melting point decreases down group 2. Moving now to the next part of the question, which is that some reactions based on group 2 metal barium are shown. So these reactions are shown and state the reagents needed for reactions 1 and 2. So there's reaction 1. Let's focus on reaction 1 first. So you had a barium metal and it got converted into a salt, barium nitrate, and hydrogen gas. Now metals only do that with acids. Metal plus acid produces salt plus H2, hydrogen gas. The acid in this case is going to be nitric acid, HNO3. So barium plus, so the reagent needed would be nitric acid. So HNO3 would be needed. And let's look at reaction 2. Barium is reacting and it's producing a metal hydroxide and hydrogen gas again. Now, metals react with water. If you add H2O to a metal, they produce a hydroxide and H2. Now, barium is down group 2, so it's very reactive. So it would probably react with cold water at a very decent rate. So barium plus H2O would produce barium hydroxide plus hydrogen gas would be given off. So over here, it's going to be, the reagent would be H2O. The next part now states that we have to name X and write an equation for its formation. So let's look at the reaction. Barium is being heated in air. Now, the only element that is reactive in air is oxygen O2, which means it's a reaction between barium and oxygen, and the compound that would be formed would be barium oxide. A metal oxide would be formed. So, let's complete that. The name of the compound is going to be barium oxide, and the equation would be that you would have barium reacting with O2 and it would produce barium oxide, and you need to balance this. So there would be 2 barium oxide molecules and 2 barium atoms. Part 3 of the question now states that barium nitrate is produced by reaction 1 is heated to dryness. So barium nitrate produced is heated to dryness. The anhydrous solid is then heated strongly and decomposes. So barium oxide is produced together with 2 other products. Identify the 2 other products of this decomposition reaction. State what would be observed. So what you're doing is you have barium nitrate and you're heating it the anhydrous solid, which means without water. So I can make an equation. Remember, all nitrates, all group 2 nitrates, they're going to decompose in the same way. So when you heat a nitrate, it decomposes, ends up producing barium oxide plus 2 NO2 gas molecules will be produced, and half O2 gas molecules are going to be produced. So identify the 2 other products of this decomposition. He's already mentioned barium oxide together with 2 other products. The 2 other products are going to be NO2, nitrogen dioxide, and oxygen gas. These would be my 2 other products. Let's now move to part 4. A given state, what would be observed when excess magnesium sulfate is added to barium hydroxide aqueous produced in a reaction? To explain your answer. Now, this is an example of ionic precipitation. Now, if you add magnesium sulfate and barium hydroxide aqueous, remember they're both aqueous. Compounds, when they are aqueous, when they dissolve in water, they dissociate. Remember, it's an ionic compound. The solid has +2 and -2 ions. They would all be joined together. It's going to be a giant ionic lattice where lots of positive and negative ions, they would all be joined together. But when you dissolve them in water, the lattice scatters and dissociates, and the ions then become mixed with water. So, for example, I have magnesium sulfate. This is a beaker and it contains water. And if I mix MgSO4, Mg +2 ions and SO4 -2 ions, they would all scatter in water. They would dissociate, and all the ions would be randomly mixed in water. Similarly, barium hydroxide is also aqueous. If you mix barium hydroxide in water, it's also going to dissociate. So you'll have the solution would contain lots of barium ions and lots of OH ions. They would all be scattered around. So all these OH ions, barium ions, etc., they would all be scattered around in the solution, dissociated form. So this is what happens when you mix a salt and a base. Remember, there's no reaction that you have studied. A base does not react with a salt in the conventional way. So what's going to happen is ionic precipitation. Both of the ions are going to mix around in the solution. Now, these ions are going to randomly combine with each other. Remember, a positive ion would always combine with a negative ion. They're going to attract each other. So don't combine 2 positive ions together or 2 negative ions together. So these ions would be mixing around, randomly colliding with each other, and they would be joining with each other. Now what happens is, if Mg and OH ions, they combine. So there are lots of Mg and OH ions in the solution. So if Mg and OH ions combine, remember MgOH2 is insoluble. So they would start forming a precipitate at the bottom of MgOH2, which is insoluble. And it's a solid. So all these magnesium ions and all these OH ions, they would start forming a solid MgOH2. And the same pretty much would happen with barium ions and sulfate ions as well, if they start combining with each other. So for example, these barium ions and sulfate ions, if they start combining with each other, barium sulfate is also insoluble, so they would start forming a precipitate at the bottom of BaSO4, which is going to be in solid state. So barium sulfate is also insoluble, GOH2 is also insoluble, so this is called precipitation. If you mix 2 of these soluble substances, their ions are going to mix around and they're going to randomly combine with each other, and they would start forming these insoluble precipitates of barium sulfate and magnesium hydroxide. And both of these precipitates would be white solids because group 2 compounds are white in color. So the answer to this question would be that white precipitates would be formed of magnesium hydroxide and also barium sulfate because both of them are insoluble. The following question reads that some reactions are shown based on methyl propan 2-ol. So this molecule is given, and for each of the reactions state the reagents, the particular conditions required, if any, and the type of reaction. So we need to fill this table, and this is provided that each reaction may be described by one or more than one type, and these words are given. These are the reaction types, and we have to label each reaction, starting with reaction number 1. If you go and look at reaction number 1, reaction number 1 is this methyl propan 2-ol. The OH part, this OH over here, is changing into Br. There's only one way to change OH into Br, and that is you will use red phosphorus and bromine. So this is for reaction 1. These are the conditions for reaction 1. And this reaction 1, we have to give it a type as well. Now, based on the following types that are written over here: hydrolysis, dehydration, substitution. Substitution is the only term that fits properly in describing this reaction, because as you can see, there is OH, and on the other side that has been substituted by Br. So this one over here is a substitution reaction. Now, moving to reaction 2, you have a halogenoalkane. Bromine gets substituted by OH. Now, this is a nucleophilic substitution reaction. Again, this one is also substitution, and the conditions for this are NaOH, aqueous, and reflux would be used. OH would provide the OH minus 1 nucleophile. So this reaction is also nucleophilic substitution, or you can also call this hydrolysis, because it's basically a reaction, any reaction in which water is involved. Remember, OH ions are part of water. So OH ions, when they substitute, this could be called hydrolysis. It's a hydrolysis reaction. OH minus 1 gets repels the bromine, knocks it out, and takes its position. Now, moving to reaction 3, you would notice that an alcohol gets converted to an alkene. So this is dehydration. The OH ion gets removed. The OH gets removed, hydroxyl group gets removed, hydrogen gets removed from a neighboring carbon atom, and the two carbon atoms then form a double bond. So this is dehydration, and the conditions for dehydration are concentrated H2SO4 will be used to dehydrate an alcohol, so an alkene would be formed. Now, moving to reaction 4, if you look at reaction 4, you're going to notice that this reaction has two different products that are forming. Now, obviously the two products are pretty much the same. If I draw this molecule, let me draw this molecule first. So this is the original alkene. Remember, alkenes usually just have addition reactions. The double bond breaks, it changes into a single bond, and two different things get attached to it. Now, over here, if I look at the two molecules and draw the structure of these two molecules, then you will notice that an HBr molecule is basically getting attached. An HBr molecule, if it gets attached, then the H would get attached to one of the carbons on the double bond. So it could either be this carbon atom or it could be this carbon atom. So one carbon atom bonds with H, the other carbon atom bonds with Br. But the position could be different. So you're going to get two different products. Let me draw the structure of the two products. So if you'll have a look at these two molecules, let me draw the product with HBr. The double bond will get converted into a single bond. So that's gone into a single bond, and H gets bonded to one of the carbon atom, a Br gets bonded to the other carbon atom. The other option could be that the H would bond to the carbon on the right, and the Br would bond to the carbon on the left. Now, if you look at this molecule over here, there's a carbon, central carbon atom. This double bond gets converted into a single bond. So there's a central carbon atom, and there are three CH3 methyl groups. This one over here is also a CH3 group. So around this molecule, there are three CH3 groups, a carbon with Br. So it's going to be this molecule over here. And this other molecule over here, you will notice that it's two CH3 groups. So that's CH3 twice, followed by CH. And then there's CH2Br. So this is this molecule over here. So both of these molecules can be produced you're going to get a major and a minor product. So the final reaction, reaction number 4, would be a reaction with HBr. So now what I just need to do is, for each of the reactions, state the reagents and the particular condition. So I need to fill this table, which is given over here for reactions 1, 2, 3, and 4. I would need to give the reagents and conditions, and I also need to mention the type of reaction as well. So here I've written down all the reagents and conditions that were for reactions 1, 2, 3, and 4, which we have already discussed in detail. So the other thing that I need to do it now is I need to also mention the type of reaction. There's 6 options given, and there's hydrolysis, dehydration, substitution, oxidation, addition, and condensation. So I'm going to mention what each of these reactions, which description best fits each of the reactions. So let's try and write down the descriptions. So I've mentioned all the reaction types. These two reactions, 1 and 2, both can be described as substitution reactions. For example, in reaction 1, the OH is getting substituted by Br, and the reverse reaction, which is reaction 2, the Br is getting substituted by OH. So this is substitution, both forward and backward. This reaction over here using concentrated sulfuric acid is a dehydration reaction. The OH gets removed and an alkene is formed. So this is a dehydration reaction, whereas this reaction 4 is an addition reaction, where an HBr molecule gets added to the double bond. So this over here is an addition reaction. So these are the descriptions, and I'm now going to fill the table with the suitable types of reactions, giving them a suitable description. So here I've written down all the descriptions of each of the reactions. Substitution, the second one is also substitution, the third one is dehydration, and the fourth one is addition. Now moving to the next part of the question, we are now supposed to draw a diagram to show the SN1 mechanism of reaction 2, including all the necessary charges, dipoles, lone pairs, and curly arrows. So we're basically talking about reaction number 2. If we go back and have a look at reaction number 2, then this is the nucleophilic substitution, where a bromine atom gets substituted by an OH or hydroxyl group. So we're going to try and draw the reaction mechanism for that particular reaction. Now in the first step, I have this tertiary halogenoalkane with bromine. This alpha carbon is bonded to, on all sides it's bonded to carbon chains. So the nucleophile, which OH-1, which is OH-1 in this case, is not able to come close to this carbon atom. So what happens is, this carbon, although has a slight partial positive charge, this bromine is partial negative. It's a polar bond. Now the positive carbon is surrounded by very large groups or chains, and the nucleophile cannot directly approach this carbon atom. So in the first step, what happens is that this bond over here heterolytically breaks by itself. During collisions, this is a slow step. You have to wait, you have to give this molecule kinetic energy, so that during collisions, this bond automatically breaks. So here I've shown the formation of a carbocation and a Br-1 ion that is formed because both electrons go towards bromine. Once this bond is broken, now there's room where the nucleophile can sneak in and bond with the positive carbocation. So the OH-1 in the next step brings its lone pairs and bonds with the carbocation, producing the product. So here I've shown the formation of the OH bond. Br-1 has already been knocked out. So this is your SN1 mechanism, which is a two-step mechanism, where the first step is a slow step, because you have to wait for the carbon-bromine bond to break heterolytically. And the next step is a fast step, because once the carbocation is formed, it has a positive charge. The OH-1 sneaks in and bonds with this carbocation. The negative charge and the positive charge are going to attract each other very strongly. So this one is going to be your fast step. So it's a two-step reaction, which is shown over here. So this is the SN1 mechanism that we had to draw in this part. In the next part, the question states that 1-bromobutane is a structural isomer of the product of reaction 1, and you're supposed to define the term structural isomer and name 3 different types of structural isomerism. So the first part is the definition of what a structural isomer is. So definition of structural isomer is that they are molecules having same molecular formula or the same number of atoms but different structural formula, so the arrangement is going to be different. Now moving to the next part is I need to write down the different types of isomerism or structural isomers. Three types are chain isomerism, where the chain could be different. The carbon chain could be arranged in different ways. Functional group could be different. For example, aldehyde and ketones are functional group isomers of each other, or carboxylic acid and esters are functional group isomers of each other. The last one is positional isomer, where the position of different groups could be different. For example, OH group could be bonded to the first carbon atom. It could also be bonded to the second carbon atom. So these are the three different types of isomerism that can exist. Now, moving to the next part, the question now states that 1-bromobutane is treated with the same reagents as in reaction 2. Butane 1-ol is formed. Identify the mechanism of this reaction. Explain why this reaction proceeds via a different mechanism than that of reaction 2. The mechanism for this particular reaction is called nucleophilic substitution, and specifically the mechanism is SN2 mechanism, and I'm going to draw the SN2 mechanism for this reaction. Now I've drawn 1-bromobutane over here. This is a primary halogenoalkane. The primary halogenoalkane, the mechanism is different because carbon, this partial positive carbon, this alpha carbon in the middle, is not surrounded by a lot of carbon chains, as in the previous mechanism that we drew just a moment ago. So the only hydrogen atoms attached. So this positive carbon is very much visible. And if a nucleophile, for example, if you have an OH-1 nucleophile, if it gets attracted to this positive carbon, it can directly approach that positive carbon atom, and the electrons in the bromine bond are going to be repelled further away because of the negative charge coming from OH-1. So this positive carbon atom is very exposed, not a lot of carbon chains around it, only one carbon chain. The OH-1 directly attacks this positive carbon atom. It's able to get close to it. And as it approaches this positive carbon atom, the bromine electrons on the other side, they're going to get repelled. And a transition state would be formed. Transition state is going to look like this. Where you have this alpha carbon, the OH-1 nucleophile would be bonding with this carbon atom. It would be coming close to this positive carbon atom, whereas the electrons from the other side would be at the same time, they will be repelled, and this bond would be lengthening, it would be breaking away, this bond would be shortening, and it would be forming this bond. And in the next step, this transition state, the process completes. Bromine is knocked out, it takes away its electrons, and OH is going to take its place. The reason why this particular mechanism, this SN2 mechanism, is followed in this particular reaction is that no stable carbocation is formed, as carbocation has very few electron releasing alkyl chains. So this is the description that you're going to write. The reason I'm using this description is, remember that you had a positive charge on this carbon atom, and this carbon atom, because it was very exposed, it had a strong positive charge. It attracted the nucleophile immediately. OH-1 was able to attack it directly. The reason I've written that there are fewer alkyl chains is that if you have more alkyl chains, these alkyl chains have a lot of electrons in them. Now the electrons over here will get attracted to the positive charge over here, and they will reduce the charge density, and in that case the OH-1 will not be attracted. So one of the reasons why this mechanism is followed is because it has very few alkyl chains, which makes the positive charge very, very strong. If there were carbon chains on this side and over here as well, then those carbon chains would have electrons as well, and those electrons would be surrounding this positive charge, and this positive charge will get neutralized to quite an extent. So this OH-1 in that case will not be directly attracted to this positive carbon atom. So this is a statement that you're going to write, that no stable carbocation is formed, as carbocation has very few electron releasing alkyl chains around it. Moving to the next part of the question now states that the product of reaction 3, methylpropene, does not show stereoisomerism. Give 2 reasons why methylpropene does not show stereoisomerism. Now, methylpropene is, you have, the first thing is that the main chain is propene. So I'm going to draw propene, 3 carbon atoms with a double bond. Then you have methyl branch attached. So there's 1 carbon atom branch attached somewhere in the middle. So this would have 3 hydrogens, this will have 3 hydrogens, and this over here will have 2 hydrogens. Now let me draw a 3-dimensional correct arrangement for this. Now here I've drawn the exact 3-dimensional arrangement. Carbon over here would be trigonal planar. This carbon atom over here would also be trigonal planar, so I've arranged them in a fan-shaped manner. This is the correct three-dimensional arrangement. The reason why it will not form cis-trans isomerism is that both groups bonded to the carbon atoms, they are exactly the same. So even if I switch the position of these two groups, the H is pointing upwards, this H might be pointing downwards as well, but it would not make any difference because the molecule would still remain exactly the same. So cis-trans isomerism will not exist. That C in C double bond C, they are bonded to the same groups. So no cis-trans in this case. Plus, there's not going to be any optical isomer because there's no chiral center. For a chiral carbon atom, you need a carbon that is going to be bonded to four completely different groups, and it would have a tetrahedral arrangement. In this molecule, there are no chiral centers. This carbon is making a double bond. These two carbons are also making double bonds. This carbon is bonded to three hydrogens. So I need a carbon that is forming single bonds only with four different groups, which is missing in this case. So the second thing is that there is no chiral carbon, so it can't form optical isomers or mirror images. So no chiral carbon in this molecule. In part 2, the question now states that methylpropene can be polymerized to form a polyalkene. State the type of polymerization and draw the repeat unit of the polymer formed from methylpropene. The first thing is this type of alkenes undergo addition polymerization. So the type of polymerization is addition. And we're going to start off with propene. The rule is, let's draw propene first. This is propene, 3 carbon atoms, and it's methylpropene. So there's going to be another carbon atom, 3 hydrogens with this. 3 hydrogens, the middle carbon has all its bonds complete. And this carbon atom would have 2 hydrogens attached to it. Now, the rule for drawing isomers is that you should draw the double bond and there should be nothing on the left or right side of that double bond. So what I'm going to do is I'm going to take this H, which is on the right side of the double bond, and I'm going to bring it downwards. Similarly, I have this CH3 molecule over here. What I'm going to do with this CH3 is, instead of being on the left side of the double bond, I'm going to bring it upwards. I'm going to bend the molecule. So you have to redraw the molecule, and once you redraw the molecule, it's going to look something like this. There's going to be double bond, and if you look over here, there's an H over here and an H on the right side. This H on the right side should be brought downwards. So instead of the H being on the right side, I'm going to draw the H downwards. Then you have the CH3 below, and then there's another CH3 on the left side, but not on the left side, bring it upwards. So this would be your monomer, and I'm going to draw a polymer out of it. And the polymer would be that you will have lots of molecules like this. The double bond would break. So let's get rid of the double bond. And the molecule would start connecting with other molecules that would be exactly the same. So this would be the repeat unit. This thing would keep on repeating. Different monomers would get connected together. The double bond is going to break and they would all be joined with each other. So this is your repeat unit. In the next part of the question, we now have to state the difficulty associated with the disposal of polyalkenes. The difficulty is, it's a 1-mark question. They are very unreactive. They're unreactive and non-biodegradable. So they don't naturally react with substances. The reason they are unreactive is because they're mostly non-polar carbon chains, and if a molecule is non-polar, it's not going to attract a lot of different groups, nucleophiles or electrophiles. So it's very difficult to break it down in the environment. So they are unreactive and they are non-biodegradable. In the next part E of the question, we have to name the 2 products of reaction 4. The first one is we have to name this molecule. Now, to name this molecule, I need to first draw this molecule. So let's try and draw this molecule. I'm going to focus on this carbon atom. It's bonded to 3 carbon chains. So there's a CH3, another CH3, another CH3. So 3 carbon chains, and it's also bonded to bromine. So let's try and name this. The longest carbon chain is 3 carbon atoms. So that's your longest carbon chain. So I'm going to call it propane. Let's call this propane because it has 3 carbon atoms. And then you have these branches. There's a bromine branch and there's a methyl branch. 1 carbon atom branch is called methyl, and this branch over here would be called bromo. Alphabetically, bromo would come first, so it's bromo. And then you have methyl, and you have to tell the position. It's 2-bromo and 2-methyl. Both the branches are on the 2nd carbon atom in the middle. So the name of the molecule would be 2-bromo 2-methyl propane. So that's the name of the first molecule. Let's move to the second molecule. If I try and draw the second molecule, the second molecule, again, let's start from this end. There are 2 carbon atoms. There's a bromine at the end, and over here there are 2 CH3s. So that's 1 CH3 and another CH3, and let's complete the hydrogens 1 with this. 2 would go with this. So this is my molecule, and the longest chain is this straight chain over here. This is the longest main chain. It's 3 carbon atoms. So again, it's propane, 3 carbon atoms. And again, it has a methyl branch, 1 carbon atom branch, and a bromine branch.